In this video, we'll discuss what is energy equation or Bernoulli's equation and application of this equation in fluid dynamics. The energy equation represents the conservation of energy of a fluid element. The law of conservation of energy states that total energy is constant at any point in a given system. So when we say total energy, it is the combination of different forms of energy. So total energy is the combination of different forms of energy. In fluid flow, there are three basic energies: pressure energy, kinetic energy, and potential energy. These energies are generally expressed in terms of head, so in terms of energy head, rather than expressing in terms of total energy. We express this in terms of head of water. So 1 meter of water, or 1.5 meter of water, or 30 meter of water, and so on. And these three heads are pressure head, velocity head, and elevation head. So this is elevation head, this is velocity head, and the third one is pressure head. So total energy or total head at any point is the sum of these three energy heads. So when we talk about this point, the total energy is sum of these three energies at that point. Similarly, at this point, the summation of these three energies at that point. So in terms of calculation, the meaning of energy equation is to equate the energy of water particle at any one point. So when we calculate the when we use the energy equation, that means we want to equate the energy between 2 points. So energy at section 1 should also be energy at section 2, because the energy can neither be created nor be destroyed. So total energy needs to remain same at these two sections. So that means that energy at a point remains the same as its upstream or its downstream another point. Okay, so energy at this section should be same as energy at downstream end, which is number 2, or energy at its upstream end, wherever it is, unless there is no addition of energy, right? So we can add the energy in the system by, for example, using the pump. So when you add the pump in the system, then we add the energy. And similarly, we may lose the energy when the water flows. There would be some frictional loss, and that if we have that, then we need to deduct. So considering there is no loss of energy and there is no addition of energy, then the total energy at section 1 should be the same as in section 2. So when we consider this moving of one particle, if there is a bifurcation or trifurcation of the pipe, so from one pipe, maybe you have like two multiple pipes or three branches of the pipes and so on, the concept still remains the same. It is about the energy of one particle, energy of a water particle at section 1. It may be later in branch number 2 or branch number 3 or branch number 4. The energy at 1 and energy at those points should be the same. Now the figure here shows the energy of constricted and expanded pipe area. So this normal pipe area, it is constricted here, and then again it is expanded and goes back to the normal. The total energy at any section is the summation of velocity, pressure, and elevation head. So at section 1, it is the summation of elevation head. So that means from some assumed datum level, what is the elevation? So that is the elevation head, the height, the velocity head, which is represented by Vn square by 2g. So this height is velocity head, and the pressure head, which is P1 over rho g. Okay, so if we poke a hole and then put this tube here, then the water level rise up to that point, and that is the pressure head. In section 2, the elevation head remains the same. You can see if you compare section 1 and section 2, the elevation head remains the same, but because the flow area is constricted, some of the pressure head is converted to velocity head. You can see this is the pressure head, and pressure head is significantly reduced, whereas the velocity head is increased. So why? Because when the area is reduced, the velocity has to increase to pass the same amount of flow, which means head will be increased, and to balance that, the pressure has to decrease. Same in the third section, the total energy remains the same. So total energy, all these 3 points are the same, but due to expanded area, velocity head decreases. If you compare with section 2, velocity head decreases. So the velocity head is only this, whereas the pressure head increases. Now, when we calculate, when we equate the energy between 2 sections, when there is a flow, there will always be some kind of head loss, and we need to include that in our equation. So ideally, in an ideal fluid, there will be no head loss, but we are always dealing with the actual fluids. Then that means there will be always some kind of energy head loss. So if you look at section 2 and 3, this is shown here. Obviously, between 1 and 2 will also be some kind of energy head loss, and so the total energy would be elevation head plus pressure head plus velocity head plus the head loss tube in the point in between. Energy line and hydraulic grade line are 2 important lines in hydraulics. Okay, so when we talk about the total energy, there are 2 lines. One is energy line, and the second one is hydraulic grade line, and they are very important in hydraulics. The energy line or total energy line gives the total head available to the fluid. Okay, this is the summation of all 3 different heads. At this point, elevation head plus pressure head plus velocity head, and similarly at section number 2, elevation head plus pressure head plus velocity head. That is the total energy line, okay, or energy line only. The next is called the hydraulic grade line. Hydraulic grade line is a line produced from the sum of pressure and elevation head. So elevation head and pressure head only, not the velocity head. Okay, only elevation head and pressure head. Okay, and similarly in section 2, elevation head and pressure head. Same in this figure here. The total head is summation of all the 3 figures, and elevation, the hydraulic grade line is the line that connects only the elevation head and pressure head. So if you draw a line here, so connecting this point, and here this hydraulic grade line would be here. So elevation head here plus pressure head here, and at this point here, right? So if you draw a hydraulic line here, so you'll see like this, connecting to this point, and here again to this point, right? So this is called the hydraulic grade line. So there are a few important points to remember. First, the energy line will be horizontal. So total energy line is horizontal along the streamline. Okay, so that is one thing. Total energy line, provided there is no head loss. Okay, or you need to include the head loss in your calculation, like this. If you add the head loss also, then total energy line will be horizontal. Next, the hydraulic grade line will not be horizontal. Okay, if the fluid velocity changes along the streamline, because when the velocity changes, then pressure head has to change. Okay, so for example, here the elevation remains the same. Now, because the cross-section area of this pipeline changes, that means the velocity has to increase, and velocity head will be increased, and that makes the pressure head decrease. Okay, so that's why you don't see the horizontal hydraulic gradient line even in ideal fluid. Okay, when there is a change in the cross section, there will be change in the velocities, and the hydraulic gradient line will not be a horizontal line. Next, in real fluids, energy lines are not constant. So here we see energy line is constant horizontal, but actually they are not constant, right? Because there will be always some kind of frictional loss, and if you want to make that energy line horizontal, then you need to add the energy loss as well. So as you calculate the total energy at any point, you need to calculate the energy loss from its upper section to that point. So you need to add that loss also in the calculation of total energy line. Now let's see another example here to draw energy line and hydraulic gradient line. In section 1, so this is the top of the reservoir, and there is no flow of water, which means the velocity is 0, right? So velocity is 0. At the top level, the pressure is atmospheric, so the pressure is also 0. So the total head at this point is only the elevation head, because the total head is the summation of elevation head plus pressure head plus velocity head. But because both velocity and pressure are 0, the total head actually is the elevation head only. So at this point, head equals to Z1. Now, when water flows inside the pipe, this some of the elevation head has to be converted in other forms of energy, and that's why in section 2 you have the elevation head of Z2, you have the pressure head of P2 over gamma, and you have the velocity head of V square over 2G. So how much will be the velocity head depends on what is the cross section of the area, right? Now, in section 3, pressure, you can see this is exposed to atmosphere, right? So the pipeline is exposed to atmosphere. That means the pressure at section 3 will be 0. So atmospheric pressure is always 0. So whenever water is exposed to atmosphere, the pressure would be 0. So at this point, pressure is 0. Elevation is constant. So if you compare with section 2 and section 3, it's the same elevation, which means the all the energy has to be converted. This pressure head and velocity head has to convert it to velocity head only, because pressure at that point would be 0, right? So the total energy at this point will be the summation of this elevation head plus velocity head, but the pressure head is 0. Okay, now let's look at a figure here. The figure shows the sewer overflow. When this happens when the hydraulic grade line of a sewer line goes above the ground level. If you have this hydraulic grade line, and if the pipeline is like this, then water goes out to the street. So one of the criteria when you design your sewer system is to check hydraulic grade line and ground elevation. Okay, and you need to ensure that hydraulic grade line is sufficiently below the ground as required by the local water guidelines. So that's one of the criteria. So when you draw the longitudinal section of the pipe. Okay, we have the longitudinal section of the pipe, and you also need to draw this hydraulic grade line. So whatever hydraulic grade line is, you need to draw the hydraulic grade line, and then make sure that hydraulic grade line is above the minimum level as defined by the council.